Dumitrescu, and she will talk about graphs to cohomological field theory.
I would like to first thank the organizers for the opportunity to speak. The aim of this project was to construct a combinatorial model of cohomological field theories that would be compatible with the topological recursion, and this means like 2g minus 2 plus n, involving a reduction on 2g minus 2 plus n. So I will explain how to construct a cohomological field theories on Riemann graphs, and using also a kind of categorical language. So first I'm going to explain the 2D CohFT and how to approach it in this language. And here I introduce the notation. A is a Frobenius algebra. If A is a Frobenius algebra that is commutative, unitary, finitely dimensional, and eta is the Frobenius form, and I choose a basis for the Frobenius algebra, and these are the notation for the Frobenius form evaluated on the element of the basis, and yeah, this is the inverse matrix. And for any Frobenius algebra, there exists uniquely a multiplication and co-multiplication. I will use also the language of vector spaces. So I'm going to recall from yesterday that RGN is the set of metric Riemann graphs, and I'm not going to introduce it again, but this is a real orbifold that is isomorphic to MGN times R plus to the n. So in particular, the space-symmetric Riemann graphs have the same cohomology to the MGN. So this, yeah. So topologically, they have the same Euler characteristics. So I'm going to, I'm not, yeah. So Riemann graph was introduced yesterday. So Riemann graph is a graph on a surface with cyclic order at each of the vertex, but labeled faces. So mainly each Riemann graph will recall a Riemann surface of genus G, and F is the number of faces, while I'm going to also use the cell graph. So maybe I'm going to define this. So a cell graph is going to be maybe the dual of a Riemann graph. So it's a Riemann graph itself, but I'm going to label vertices. So this lives on a Riemann surface of genus n, and then n mark points or n vertices. So for me, yeah, I'm going to denote mainly gamma gn to be such a cell graph. So now I want to define the two-dimensional topological quantum field theories. So I'm going to introduce, well, there is an operation that I can construct on these cell graphs, and the operation is I take a cell graph and I'm maybe, yeah, of the type G and N, and I can contract one edge, and I get something like this. A cell graph of genus stays unchanged, and the number of mark points goes down by 1. Or I can have a cell graph and I can contract a loop. So if I can contract a loop, usually there are two cases here. Whenever you get is disconnected, if you contract a neck loop, or connected. But what happens is that I'm going to separate this into parts, and here is how I contract the loop. So I'm going to construct now a category, the cell graph category. So this is a category of monoidal category of cell graph, where the objects are a finite disjoint union of cell graphs, and morphisms are given to objects. It's the sequence of edge contraction operations that you can form from one to the other, if they exist. So all edge contraction operations from one cell graph to the other. So I just want to emphasize now that all these cell graphs represent the DNA of a Riemann surface. So there is a Riemann surface behind. And when I say that I contract this edge, what it really means is that I apply like a pair of pants decomposition that corresponds to that Riemann surface, that corresponds to this multiplication. While if I say I want to contract this loop, it's the same. I can apply kind of a pair of pants decomposition that would correspond to the co-multiplication of that Frobenius algebra. Yeah, if I have a Frobenius algebra. Now I'm going. So this is the self-graph category, and now I want to introduce a 2D CohFT functor. So I want to introduce first. I need. I'm not going to start with Frobenius algebras. I'm going to start with vector bundles. So I'm going to introduce V epsilon eta to be the monoidal category of finite dimensional vector spaces that come in pairs V and the trace and the bilinear form. So these are the objects of the category, and morphisms corresponds to, well, if I have two objects, then I just aim for linear transformations that makes a certain diagram commutative. And on the other hand, I'm going to denote V over K to be the category of K objects. And this consists of vector spaces. Yeah. So K will, it's the ground field. Yeah. So this consists of vector spaces that come with a trace, like this, and the morphisms corresponds to such commutative diagrams. And now I want to introduce 2D CohFT.
I'm sorry, so just going back before you erase it, so I don't understand your morphism. So if this, because you didn't contract the cycle, so if this goes from, the top one goes from gamma Gn to gamma, nothing happened, right? I mean, you just
genus didn't change, just one of the vertices disappeared.
The number of vertices, okay.
Yes. While here I have like two possibilities. So either I split either is disconnected in. So then the genus splits, so that will be like living on genus G1 and G2, so that they have to genus G. And then the number of mark points, it's.
But and how do you decide if it splits or it doesn't split? It's just if they're next to each other or if they're not stable. So how do you decide if it splits or not? Or does it always split?
No. So for example, if I have this, I can have something like this, and in this case it doesn't split. So I get I get just one. If I contract it, I don't disconnect the surface. But if I have like something like this, then in this case, if I contract it, if I contract it, let me make another drawing. So let's say I have something like this, something here, and I have this loop. So in this case, then it's disconnected. Okay, so I'm going to define a 2dt CohFT to be a monoidal functor small omega from the monoidal category of cell graphs to the functor category of the monoidal category of fine dimensional vector spaces and K objects. So what is this? Well, to every such cell graph, I'm going to associate a functor that, if I start from a pair of a vector space with a trace and bilinear form, then this is going to give me v to the n and a map from v to the n to k. So n is the number of vertices. So this is how it acts on objects. And then how does it act on morphisms? Well, the morphisms here are these cell graphs. So what I can, I ask that, that mainly edge contractions operations are compatible with mainly multiplication and co-multiplication of the Frobenius algebra. So mainly I can have some. So I'm going to just do the basic examples. If this is a Riemann graph of genus 0 with 2 vertices, then this is going to give me a map from V tensor V to K, and this is going to give me a map from V to K. So then I will associate to this the multiplication, and then I ask that this diagram is commutative. While this is the first situation, while if I have a loop, then this will be 0, 1. Then I can contract a loop and I get 2 distinct points. So the loop is going to give me an assignment from V to K, and these 2 distinct points will give me an assignment from V tensor V to K. And what I'm going to ask is, so this will be like the image of this. So I'm going to ask here that this is going to be given by the co-multiplication, and this will be by this. So, and then it can be generalized to any graphs. Okay. Then I want to. Then the theorem is that starting from any such to the starting from so the theorem is that if V, epsilon, and eta is an element of V, epsilon, eta, then I can associate the trace to be the image of this point, then the bilinear form to be the image of this, and also I will associate the multiplication to be the image of this, and the co-multiplication to be the image of this. So if eta is if eta is non-degenerate, then V becomes a Frobenius algebra that is commutative and co-commutative. So this is the first part of the theorem. And the second part of the theorem is saying that if eta is again non-degenerate, then this is independent of the choice of the Riemann graph of the cell graph I'm starting from, and it just depends on the topological information of the Riemann surface where this cell graph lives. So the second part of the theorem gives that gives that if gamma gn is a connected cell graph of type GNN, and V is the vector space so that eta is also non-degenerate.
Yeah, excuse me.
So, sorry, yes.
With the theorem, if you do it like epsilon and eta are already given, but it's a given notation, right?
Yeah, yeah.
Notation meaning that epsilon eta is not chosen when you choose an element, right? You just choose an any
Yes.
object. Then you define
Yes.
corresponding, So that epsilon and eta
Yeah.
not.
Oh, sure.
Right.
Yeah, so something like this, yeah.
Right.
Yeah.
That's what I meant. Yeah. Then it becomes right.
Then any 2D CohFT functor just depends is the trace of the product times the Euler element to the power g. So the Euler element is going to be the multiplication composed with the co-multiplication of 1. And maybe I can emphasize a little bit the proof of this result. So this does not depend on the graph. It's independent on the graph. It only depends on the number of n of genus and the Euler element. So to emphasize the result for like a short proof for any ribbon graph, if the ribbon graph is connected, what I can do is to contract all the edges until I get like a fat point with a bunch of loops that will recall me the genus. So when I contract the all edges, I should have said that, so cell graphs I denote like this, but if I talk about 2D CohFT or cohomological field theories, I think about these cell graphs with these are functions, and this is information of V1 and V2, or information of elements of the vector space or the Frobenius algebra attached to each vertex. So for me, this will represent the 2D CohFT. So I'll have these elements attached to each vertex, so I can contract all the loops. So this means that I can contract all these edges, and this means that I'll get like the product of all elements. And here I may get a bunch of petals. Okay, so I may use this because I may actually use it later. So what happens is that if you have a ribbon graph, and then you have maybe this I'm going to denote by V, and this has one this loop attached to it. What I can do is this is the same as this, and now I can apply the co-multiplication, and I'm going to disconnect these two. So if I and then I can move this into you can move into the CohFT here, and it becomes 1 again. So this is the same of V and 1. That is the same with V. So actually it doesn't matter if you have a loop there. So you can simply eliminate it from the object. But what it matters is this kind of loop here. So this is a loop that, and this I want to emphasize that it brings a contribution of G. So if I contract this, it will my result will bring a contribution of each of these of an Euler number, and I want to maybe do this because I'm going to use it later. So for example, I may start from a self graph like this, and here I have a loop, and I can interpret this as, well, this is V and this is 1, and now I can apply the co-multiplication, and I'm going to get something like this, and then I'm going to apply the co-multiplication. So these are these two pair of pans, And I may get something like this. This is still V, but this is going to be, this element will be M composed with delta of 1. That was the Euler element. And then I apply the multiplication again. That gives me V times E. So this shows that, that if I have such a loop, I can eliminate each of the petal, but the price I pay is that I'm going to multiply, multiply the result by an Euler element. And now I can imagine that if I live on a Riemann surface of genus G, I have G such petals, so I'm going to multiply this by e to the G, and this is where this is coming from. Okay. Now I want to play the same game with cohomological field theories. So I want to introduce a similar set of axioms and a similar interpretation. This is a classifying result. And of course, all the TFTs are classified by the Frobenius algebra. But I want to kind of apply the same technique for this combinatorial model of cohomological field theories. So, you can do it for nodal curves, for smooth curves, or for ciliated. So I'm going to for S1 for bundles over this. So I'm going to use to define over ciliated ribbon graphs. So assume I have a ribbon graph, and I'm going to define a ciliated ribbon graph. A ribbon graph with a cilia added on each of the faces. So I want to assign one boundary point on to each face, and in order to know what the face I'm talking about, I'm going to put this cilia. So I'm going to place one point on the boundary with 1 point on each face. So this is an S1 to the n bundle over RGN. Now I want, so cohomological field theories have this target. So I want to mainly introduce them for smooth. I mean how to glue smooth curves. So I'm going, the combinatorial model will involve the ribbon graphs, and I'm going to because they have the same cohomological information. So I'm going to now associate to each cell. So each cell graph has a dual that is a ribbon graph, and all the this set of edge contraction operations will introduce some operations on this other set of ribbon graphs. So what are the operations induced from the cell contraction operation of the cell graph that are Poincare dual? I want to explain. Okay, so I want to construct non-singular curves by gluing non-singular curves. So in a way that is compatible with these edge contractions operations that were pairs of pans upon decomposition of the ribbon surface. So so I have this. So this is a metric ribbon graph, and I have one cilia associated to each of the face. And what I'm going to introduce is a map that. So from this has a perimeter. I'm going to cut in half this perimeter and associate two cilia at the midpoint, let's say. So this goes from RGN to RGN plus 1 because I increased the number of faces by 1. So this is the this is compatible with these edge contraction operations. And I want now to glue to see what corresponds to a loop contraction. So assuming I have two faces, each one marked by a 1 cilia, I'm going to introduce one edge of length 1 and introduce a cilia at the midpoint. And of course, this object can be connected or disconnected. So I can do this in two ways. I'm going to denote this one by alpha, that is corresponding to this multiplication. And here I have the two cases. Each one will be beta 1 and beta 2. So beta 1 will be the connected case and is defined a map from Rg minus 1 n plus 1 to R tilde Gn, so to all ciliated metric ribbon graphs, while beta 2 is Rg1 n1 plus 1 times Rg2 n2 plus 1 going to G1 plus G2 and then 1 plus n2 plus 1. So this means now I constructed these three maps. So this means that I have corresponding maps between the cohomologies. So this will give me alpha star, a map from the cohomology of R tilde Gn plus 1 going to the cohomology of Rgn. This one will give me beta 1 star from the cohomology of R from the ciliated ribbon graphs of type Gn going to the cohomology of ciliated ribbon graphs of type minus 1 and plus 1. And the B2 will give me a map from the pullback, from the, this is the disconnected case, and by a QNet formula is a tensor product of the two cohomologies.
So how do you choose this affiliation in the second operation? Because there are two choices.
Oh yeah, there is an S2 action. Yeah, there is a Z2 action. Sorry. Yeah, you can choose. Yeah, it's not uniquely, but this it kind of plays a role in the classification theorem. There is a So these are not the nodal gluing maps here. So now I want to introduce. So maybe before I do that, I will talk a little bit about these cohomologies of some observation about the psi classes on these objects. So I have, assuming, probably I'm going to use it only. So next I'm going to use it only when in the case n equals 1. And why I'm going to use it like this is because of this fat point petal. So if you remember the game we played here, when we collapsed the whole graph to one point, this is, but I'm going to take here so I'm going to place one cilia at one of the faces, and this is the face I. But this will be the same like Rg1 to the ciliated ribbon graph in case I have just one. And this is the map to Rgn. So there is the Gaussian sequence that gives a long exact sequence between cohomologies. So I have so the first term class is a psi I is the psi I. So I have the h2d minus 2 of Rgn multiplication by psi I goes to h2d of Rgn. And here if I take the pullback, I get to h2d of R tilde Gn. And now I take the integration along the fiber and get h2d minus 1 of Rgn. And then I can do it again by the psi I that goes to h to the minus 3 of RGNs and so on. So here, sorry?
To the +1?
Oh yeah, plus 1, I'm sorry. It just goes up by 2, not go down. Yes. So here the observation is that in the stable range, there are stability theorems that describe these cohomologies rings for MGN. So the stable range means d less than 1/2 times g minus 1. And this means that the cohomology up to degree 2g of moduli of smooth curves of genus G and rank n is the filtered part of degree 2d of the ring where I have here the free generators of the psi classes and then the kappa classes. So in the stable range, if the genus is large enough, each of these have degree 2 and this has even degree. This means that all the odd degrees of the RGN in the stable range, so yeah, this is 0. While when you apply to this short exact sequence, this will give you that this ciliated part, if I have just one cilium here, will also be 0 in the stable range. And moreover, the pullback of the psi class will be 0. So you shouldn't expect psi classes appearing. While in the non-stable range, for example, other things can happen in the non-stable range. So for example, if I have D1 and GE1, this will be Q. And and one can describe them for small degrees. Okay, now I want to introduce the cohomological behavior. So I want to introduce cohomological field theories on this combinatorial model. So I'm going to further denote 2 to be the category of 2 objects with one morphism. So I have 2 objects that are connected. And I'm going to denote, so I'm going to introduce a cohomological field theory to be a monoidal functor from the cell graph category to the functor category from the finite dimensional vector spaces epsilon and eta to functors from 2 and v over k. So I'm just using the previous notations. And I'm just going to give, so what it does on objects. So on objects, I will have a self-graph gamma gn, and to each vector space, what it's going to do is going to send it to a map from V tensor n to the cohomology of R tilde gn. And then I'm going to ask that this is actually compatible with a degree 0 part, that we introduced it by the 2D CohFT, that's small omega. So I'm going to ask that this diagram is commutative. So this is how it acts on objects. And now it has an action on on morphisms as well. So maybe I'm just going to do these two cases that I did before and express it in some and express it by some commutative diagrams. So the cases we considered before, and here I'm not going to define it in the stable range. I'm not going to pose any condition for G and N. So for example, this point, what it does is going to send this pair to, here I have, this is this, this is the trace, and I asked that this is commutative. And if I have 2 points connected by a line, then it's going to send it. So it's going to send this vector space to the pair V tensor V, K, K, K here. And now I'm asking that this diagram is commutative. And moreover, I now have to think about morphisms. So I may have like this, this morphisms are natural transformations here. So this is going to send this pair into, well, I'm going to have a commutative diagram on top and one on the bottom. And now I'm going to connect them. Like this. And mainly this is eta, and this is the multiplication. This is epsilon, this is epsilon. So this corresponds, again, the edge contractions, that was the pair of bands decomposition. This, I want to correspond it to the multiplication of the Frobenius algebra. And the same thing for the loop, for this case. I'm not going to write it again, but it's the same pictures as this one. So, okay. So this is the definition. As an observation, there exist natural maps from the set of ciliated ribbon graphs of genus G and faces to metric ribbon graphs, genus G and N, and this goes to smooth MGN, and this is embedded into MGN bar. So cohomologically, I'm going to reverse the directions. So this means that nodal theories, so if I have a nodal theories give rise to this ciliated theories that I denote it like this. So maybe nodal theories, you can denote it like that. But actually, also ciliated theories will give rise to the nodal theories, and this is you can use them to reconstruct the nodal theories. Okay, so okay, so I'm going to now give a classification theorem for these theories that is similar to the classification theorem for 2D CohFT. And for this, I need to construct. I need to take projective limits of cell graphs. So I'm going to construct pictures. Okay. So I want to now glue projective system. So I'm going to recall that the set of ciliated ribbon graphs, if I have just n equals to 1, I can glue them and use the beta 1 to the ciliated ribbon graphs, and the genus just adds up. But I have still one face. So this gives a projective system on cohomology I will reverse the arrows. And then go to the cohomology of Gen 1. Okay, and there is and the Matz and Weiss theorem tells us that the limit when for hygienus, this is just given by kappa classes. Well, I'm just going to use that. This is the series T1 up to T1, T2, and so on. But these actually have a degree 2i. So these are kappa classes. Okay, so I'm going to use this approach and try to construct a graph with infinite, like a cell graph with infinite petals out of this, and try to go to this projective limit. Sorry?
Don't you have psi1 here? I forgot. Psi1 is 0? Okay. Right.
Yeah, psi1 is 0, yes.
Okay.
Yeah, we just proved. In general, if I have RGN, you'd expect that at least in the stable range, that will give you like the the information of MG, and then you will have psi classes. So here so at least in the filter part of 2D. Yeah. But here n is equal to 1, and this psi is 0 there. So I will start from a cell graph like this. Okay, so this is a cell graph on a torus. But I'm going to introduce a loop. Oh, maybe I need some space here. So I'm going to introduce a separate loop. So this is a cell graph. Maybe I can denote gamma 1, 1. So it will give me a map from V to the cohomology of R 1, 1. So it has genus 1 because it lives on the torus, and one face, so it lives here. And now for each of, so I'm going to add one more petal here. Now it will have genus 2 and 2 face. So this will be gamma 2, 1, and it gives me a map from V to H star of R tilde 2, 1. And what I can do is to contract the separating loop, and I will get two disconnected pieces, so I can project on one of them and get a map like this in the same way I defined. So this is now a cell graph of genus of genus 2 and one more point, but it has two faces. So now on each of the face, I'm going to introduce the same picture. So so this will be now a cell graph gamma 4, 1, and it will give me a map from V to the cohomology of R tilde 4, 1. And if I can contract this loop and I separate them, and these two pieces will be symmetric, so I will take the projection on one factor. And I can do it now for any face, so the number of faces is now 4. So it's 1, 2, 3, 4, and on any such face I can introduce this picture, and that will give me an infinite graph. So in general, there will be 2 to the there will be 2 to some power the genus and the number of faces. So that will give me in general, and I can a map like this. So I'm going to take this infinite. I'm going to take this kind of infinite cell graph where we're adding this infinite number of petals. And let me denote this by H from a Hopf algebra. And when we, so at the beginning of this lecture, I said that if I have a cell graph and I have such a loop, if I have V here, then, well, it was for 2D CohFT, but then it's a similar game. I can kind of eliminate that loop, but the price I pay is that I'm multiplying this element by this Euler element of the Frobenius algebra. But now I'm kind of doing, I'm playing this reverse, this opposite game. So I'm starting from this or something, and I want to add this petal. So in order to add this, I need actually that this Euler element is invertible in order to be able to do this. So this means that the Frobenius algebra is semi-simple when the Euler element is invertible. And you see that I kind of play this game, and I created this petal. So every time I have to multiply by E inverse to the G, where this G is the genus I'm creating. So the proposition is the following that we just proved. So let's assume that this Euler element is invertible. Assume that this Euler element is invertible. This means that V is semi-simple. Then I can take the projective limit of omega of this G1. So maybe this was G1 level. And this I have to multiply by e to minus G times V, because this is the price I paid for adding this petal. So then this defines a map that I'm going to call omega of gamma infinity and 1 from, so this was from V to the cohomology of RG1. So this map will go from V to the projective limit of this cohomology of these ciliated ribbon graphs. And by the Madsen-Weiss theorem, this is H. So this infinite cell graph will actually give me like something that will now behave like a 2D CohFT. Okay, so we have now this picture. So what we did is to start from V, and this is this Hopf algebra H. And here I have V tensor V, and here I have the product of this Hopf algebra. So this is a Hopf algebra. And on this level, this encodes the information of the Frobenius algebra, and this encodes the information of the Hopf algebra. This will be like cell graphs, while this will kind of encode a ribbon graph. So there is some sort of duality here. And this is given by omega infinity 1. This is the comultiplication, and this is also the comultiplication, and this is the product between this. So this diagram is commutative, and due to this graph property, this is an infinite graph, but the way it was constructed was that once you contract this loop, you're going to split it into two equal parts, two symmetric parts. So this infinite graph, that was gamma, so this infinite graph was gamma infinity 1. So what this tells is that once you apply this delta operation to this, yeah, I don't have, yeah. So it tells that, so that this is group-like element, right? So this omega of gamma infinity 1 is a group-like element, is the term used. And for such a Frobenius algebras, these are classified, and these are actually given by exponential of these kappa classes. Well, with some coefficients here, Ti maybe Si, I don't know, some coefficients here. Okay, so I'm going to end the talk by the theorem, by the last theorem that this homological field theories for ciliated ribbon graphs do not depend on the ribbon graph. So this is the theorem, and it's not, yeah, it's in progress. I mean, it's not yet posted, and actually is a theorem of Telemann reinterpreted. And it's saying that if V is a semi-simple, semi-simple means that E, that is this element, is invertible, then I can then all of these are going to be given on the element V1 up to Vn by this gamma infinity evaluated at the element e to the g times V1 times Vn. So this is an element in H, and it depends on the kappa classes. And the way to prove it is, yeah, you'll take a graph, and at some vertex maybe you attach this other graph, infinite graph, and then this infinite graph here with petals, and then you'll contract this one to a big fat point. So now that infinite graph carries the information of e to the g times V1 Vn, and will become now a graph with infinite many petals. But this is where this is coming from.
What is omega sub V?
Oh, sorry. Yeah, this is. Yeah, for some reason I use this notation here. So it's actually the same proof. So this is saying that actually they behave in a similar way. So this is related to the classification theorem of the 2D CohFT, and once you interpret it at this level, and yeah, probably I will stop here. Thank you.
Any questions?
Yes.
Do you have a good way to calculate this stable element thing? To calculate these SIs, I guess?
These SIs, are you asking about the reconstruction, or?
Yeah, basically.
Yeah, I think there is a way to do the whole reconstruction game. The R matrix and all the formalism. There is a way to do it on this combinatorial way, I think. But yeah, kind of figure out a way to do that.
Maybe it's worth pointing out, those are exactly the hierarchies and ones I wrote down in the formal logarithm called logical field theory. This is where I mentioned that these things are then group-like before you take the exponential and take the log, and then you get the log, and those are exactly these. This, what did we call it? Extended phase space coordinates, SI. So, and then the recursion we gave for them does that.
Yeah.
But maybe there's another way to do it now.
But yeah, my goal for this was to twist this Catalan recursion by this cohomological field theories, and we did it. We twisted by 2D CohFT, but I wanted to twist it in this, and you can use this now formalism and try to do something with topological recursion on the cohomological level. So that was, but I don't have examples. I don't have the example. Yeah. Yes.
So when you have just omega 0, 1, by doing Laplace transform with respect to the variable x, you do get a combination of kappa classes. So does that play any role?
Mm. That's a good question. Yeah, I don't know.
There's a formula how to get
Mhm.
such an element from just
Mhm.
of omega 0, 1,
Mhm.
x and 1.
Mm-hmm. Yeah, yeah. I don't know yet the whole reconstruction game.
Other remarks or questions? I just have a short remark. I mean, there's a lot of these things I actually looked at in terms of constructing chronological field theories from ribbon graphs, but we can discuss later.
Okay.
All right. If there are no more questions, let's thank the speaker again and adjourn.
Thank you.